Well, the actual question is vector potential or scalar potential really, shouldn't they have any physical consequences? So this is usually interpreted as having implying that the vector potential, in fact, has a physical consequences, the vector potential and the scalar potential. But nevertheless, although they have physical implications, we have the gauge invariance. We don't want to change gauge invariance, so we don't want to give away gauge invariance because all the Maxwell's equations and electromagnetism is based on gauge invariance. Although this phenomenon depends on the vector potential directly, it is still gauge invariant because it only depends on the total flux, which depends on B. So if we had chosen some other vector potential, we would still get exactly the same answer. And now we will see it in a more general framework that we will exactly get the same answer. Now let's just consider this case where we have this region where B is non-zero, and we send some particles over here from here. So they might go above this region or below this region. So let's say this is the point O. Now if they go above the region, we can say that the wave function will gain a phase which is given by e to power I a dot dr, a dot dl from O to F to B. Oh, okay. O to P.
In that case, there is no restriction that it could go inside the area which is.
Well, I mean, the particle is not following a trajectory if there are no boundaries. So this will be, in fact, now it will be more clear when we discuss about the path integrals. So we will see that whichever path the particle takes, this one, the above one, the middle one, the below one, all will have this phase on top of what it would have been if there were no magnetic field. Because in all these regions, the curl of A is 0, which basically implies that the integral from O to P of A dot dl is independent of path, as long as they are all above the solenoid. So basically we just say that for the part of the wave function that goes above the solenoid, it acquires this additional phase due to the presence of the solenoid. Okay, the part, this is, let's say, O to P from above, plus there's also the possibility that it will go below the solenoid, and all of them will acquire this phase from O to P of A dot dl, but this time we go from below the solenoid. Now there will be a phase difference. The phase difference will be given by O to P of A dot dl, let's say below, plus or minus O to P of A dot dl, which is above. This is the phase difference between those two possibilities, let's say. But this phase difference we can write as A dot dl, let's say below, plus from this is O to P, from P to O of A dot dl above. So we start from O, we go to P from below the solenoid, and now from P to O above the solenoid. Now that's just a loop, so we have this loop integral of A dot dl around any loop that encloses the solenoid. But this loop integral we can always write as the curl of A dot dl. Well, sorry, I forgot some dA. There is factors of Q over H bar over here. Because it will not be influenced if Q is 0. But this is nothing but our B, the integral of P over this area integral over all this area. Not only on the regions where there is the magnetic field, but over all the area that has the zero magnetic field. But they don't contribute, only the region which has a magnetic field contributes, and their contribution will be just, okay, this is Q over H bar, Q over H bar, Q over H bar, Q over H bar. That's the magnetic flux. So the phase difference is equal to Q over H bar times the magnetic flux that is going through the solenoid. Okay, the tricks that we had used, both above the solenoid and below the solenoid, this is the equation we have. This is equal to I H bar del psi by del T. Now we made this change. We said that, okay, let's say psi is equal to e to the power I Q over H bar, the integral of A dot dl from some reference point to the point R. This is at the point R and TE of, let's say, psi 0. Now the vector potential is time independent. So this integral doesn't depend on time. So the phi is not influenced by this. So what is left, phi can be, by the way, not necessarily phi. Let's just put any potential that you like. So if we just make this substitution, the equation satisfied by psi 0 is just 1 over 2m minus h bar squared Laplacian plus v psi 0 is equal to I H bar del psi 0 by del T. Well, of course, there's one catch. Now, if you want to define a function A dot dl independent of a particular path, there should be zero magnetic field. The curl of A should be 0. Otherwise, that integral will depend on the path, and hence, you are not really defining a function of the position R. It will also depend on how you go to R. That's not a wave function. So this redefinition you can only do in regions which has zero magnetic field. So that's why we are still requiring that my particle cannot penetrate the region where there is a magnetic field. Out of this region, the magnetic field will be 0. Since the magnetic field will be 0, this A dot dl integral will be independent of the path as long as you don't go around the solenoid. So that's why I separated these two phase factors, above and below. If there is no magnetic field anywhere in space, then B is everywhere 0, flux is 0.
If there is some anywhere in space,
okay,
then it will affect. If it's close or not, it will affect.
Sure. Whether you are going around the flux or not, it will affect.
Even if it's far away?
It will happen. Now, of course, up to this point, it won't be easy to see any relation with the geometrical phase or the Berer phase. There's nothing. Now let's relate this to the Berer phase. Now, Berer phase, if you remember, we should have a parameter which is slowly changing in time. If it is slowly changing in time, then we can define this Berer phase, etc. Now let's say we have this. We have the region of the magnetic field. And let's assume that we put our charge in a closed box somewhere over here. Now the position of this magnet, the center of mass of this box, let's call it R. So any point on within this box, let's just call it small r. The wave function in general will be a function of small r and the large r and even a function of time. But we can, within this box, we have the Schrödinger equation, 1 over 2m minus I h bar, the gradient minus q times a squared plus q plus v the potential. Well, let's say there's no everything is neutral, or we choose a gauge in which the scalar potential is 0, electrostatic potential is 0. Then this potential will be basically the potential corresponding to the box, which keeps the electron inside the box. And it will be a function of r minus r. This whole thing acting on psi r, large r and t, this is equal to e psi and t. No, okay, so we don't have this t over here. This is our time-independent Schrödinger equation. So we are looking for the nth eigenvalue. Now, within the box, the vector potential is everywhere 0. So I can say that within the box, I can, in a sense, trivially solve this equation. I know that I can write psi n of r and large r as a function of e to power I q over h bar, let's say from r to r of a dot dl, psi n, let's say 0, r and large r, and I'm in the box. Within the box, this psi n 0 satisfies this equation, minus h bar squared over 2m Laplacian plus v of r minus r, large r, psi n 0 of r and large r. This is equal to E n psi n of r and large r. Well, let's see. In the box, A is not 0. This is the equation we have. The phi is 0 everywhere. That's the gauge we chose. But A is non-zero. But in the box, the magnetic field is 0, so I can redefine wave function in this form. In the box, this integral over here is independent of the path. So it's a well-defined function of R. But if I make this redefinition, then this psi n 0 just satisfies a Schrödinger equation which doesn't contain the A. You see, you can also think of it in this way. We have this box, this region of space. And we are trying to write down the Schrödinger equation in this space. So what is the vector potential? The magnetic field is 0. So I can choose a vector potential which is 0. Or I can choose a vector potential which is non-zero, as long as its curl is 0. So both of them gives me the same physics. This is basically that transformation. I can describe this zero magnetic field region as zero vector potential or non-zero vector potential. I'm completely free to choose whichever one I like. It shouldn't be changing physics. So initially I have this solution, this equation, But rather than using that gauge, let's say I'm changing my gauge by multiplying my wave function with a position-dependent phase. So now I have, in my new gauge, the vector potential is 0. Now the problem is, I cannot set the vector potential equal to 0 at everywhere in space. Only within a certain region I can set it to 0. As you have pointed out, there's a magnetic field somewhere in the universe, let's say. So I cannot set the vector potential everywhere to be 0, but in a local region, in a finite region which has no magnetic field inside, I can always choose a gauge in which the vector potential in that region is 0. Now, you see, the solution of this differential equation, by the way, doesn't depend on R and capital R separately. Psi n of 0 is actually a function of psi n of only of the difference. Now, what is my time-dependent parameter? So what will I do is, I have this cube.
You change the position.
Yeah, I will just move this cube around my solenoid very slowly. The position is changing slowly. So in the adiabatic limit, there's an adiabatic process. So I can talk about the Berry phase, the geometrical phase, the Berry phase. I know the solutions. I know the solution of my wave function, of my Schrödinger equation, are e to the power I q over h bar from large r to small r, a dot dl, psi n0 of r minus large r. This is my wave function. Now let me calculate the Berry phase. Remember, the Berry phase, we related it to this matrix element. Now this time I'm taking the gradient with respect to r of this psi n. This will be equal to psi n. Well, if I take the gradient with respect to r, there are two terms that depend on r, the exponent. The gradient of the exponent will just give me minus I q over h bar a the vector potential at the point r, at the point capital R, times psi n plus psi n, I have the exponent, gradient acting on psi n. Now the first term, well, this a, the vector potential is just a number, it's not an operator, so I can just take it out. I have the normalization. Well, that is just one. So it's minus I q over h bar, a of r. Now in the second term, I can also take the exponent out. It's just a number. Psi n. Now remember, psi n is a function of the difference of the two r, the capital R and the small r. So I can write the gradient with respect to capital R as minus the gradient with respect to small r. But that is the momentum operator. The average momentum of a particle in a box is 0. So this is equal to 0. Now, although I'm slowly moving my box around, so the average momentum of my particle is not 0, in the adiabatic limit it is negligible. That is how we define the adiabatic limit. Now, gamma n was, remember, I psi n gradient with respect to r psi n dot dr. This is the bare phase.
So in this case, like it is not dependent on the shape of the A in the box. Just depends on the center point.
Yeah, in a sense.
It's because we move it slowly.
Well, you see, the shape of A is gauge dependent.
Yes.
Things cannot depend on the general shape of A.
Yeah, but A's value in R isn't it also gauge dependent?
Sure. But at the end result, the bare phase is Q over H bar A of R dot dr, which is Q over H bar curl of A dot dA, which is Q over H bar phi. You see, the matrix element itself is gauge dependent. So this matrix element over here is gauge dependent. It depends on the vector potential, which changes if we change our gauge, but not the bare phase. The phase of my matrix element, of my wave function, also depends on the gauge. But the wave function itself is not an observable. So its phase is gauge independent, so what? It's not an observable. What is observable is this bare phase. And that phase turns out to be independent of the gauge. And furthermore, for example, in this example also, you are, at least this is the hypothetical example, you are confining your box, your particle in a box. So its wave function cannot just extend until the magnetic field. So in fact, you can make two things. You can just assume that the boundaries of your box is very hard, so the wave function cannot really tunnel through. And secondly, you can just take this box very, very far away. I mean, just assume there is a magnetic field over here, some galactic magnetic field line going from I don't know where to where. You just take your galaxy to the Andromeda galaxy, your box to the Andromeda galaxy, and just move it around, keeping the distance fixed. I mean, you cannot just say that, okay, maybe there is a tail of the wave function anymore.
So if we do not move it around like a closed loop,
Okay.
and would it require like anything like a phase? It wouldn't, right?
It does. You see, let's go back to this example over here. You see, there is these, you can say that you have the wave function, part of it goes above the magnetic field, part of it goes below the magnetic field, and each part acquires a different phase. This phase is, by the way, gauge dependent. But that phase itself we cannot measure, because I can just factor out an overall phase, and the only thing that I can measure is the phase difference between these two components, the one that goes above and the one that goes below. And that phase difference is gauge invariant. Well, this transformation that we had studied last hour. Now this one. This is called gauge transformation. It's just the name of this gauge transformation. So in a sense, for a given electric and magnetic field, you have infinitely many vector and scalar potentials. We usually choose one of them to work with. But since they all correspond to the same electric and magnetic fields, they should describe the same phenomenon. At least that was the classical understanding in the Maxwell's equation level. Now when it comes to the quantum mechanics, it seems that the vector potentials, they have an influence. Even if the electric and magnetic field is zero, the vector potential themselves the vector potential and the scalar potential themselves influence the wave function. Then there is this question, should we give up on the gauge principle, this gauge invariance? So because the gauge invariance just tells us that since there are infinitely many vector and scalar potentials corresponding to the same electric and magnetic fields, before we used to think that, okay, we should only, always possibilities, different choices that correspond to the same electric and magnetic field, they should describe the same phenomena. Now we see a phenomena which kind of feels the vector potential. But nevertheless, we don't need to give up on the concept of the magnetic field, of the gauge invariance, because this additional phase, the influence of these vector potentials, turns out to be gauge invariant. It does, whether you choose one vector, if you look at these expressions, the phases that each one of the components acquires depends on which gauge you choose. No, the phases, they do depend on the gauge. But the overall phase is not measurable. The only physically measurable system is the phase difference. And that phase difference turns out to be gauge invariant. It still depends on the flux and the magnetic, or which depends on the magnetic field. But nevertheless, our charged particles never enter the region which has a non-zero magnetic field. And this effect is caused by the vector potential itself, but nevertheless the observable consequences are still gauge invariant.
A pair of scalar vector potentials called a gauge. A pair of these potentials is called gauge.
Not really. Okay, this transformation is called gauge invariance. Now we say choosing a gauge, we fix a gauge by specifying a condition on how to determine this lambda. Now in this explicit derivation over here, we assume this is our gauge, or gauge fixing condition. Okay, when you speak, people say that, okay, we will be working in the Coulomb gauge. What they mean is that gradient of A is equal to 0. That will be the meaning of Coulomb gauge. Or you can work in Lorentz gauge, for example. Lorentz gauge will just be gradient of A minus del phi by del t. This is equal to 0. You can just choose whichever one you like.
I think this has to be without T.
No, it has to be with T.
We checked it. We checked it. This is actually, we found this Ludwig Lorentz, not Lorentz.
Oh, the name. Okay. Okay.
It is interesting, but it is so.
Okay, I always check it also, but I always forget which one was which one. Okay. I was thinking that you were talking about the same T. No, I agree it's a weird phenomenon. I cannot claim that I understand it. But it just seems to be so.
Increase the dimension without needing it. So, to solve the equations, we introduce some maybe unphysical parameter, and then we set another condition to basically calculate for the vector and scalar potential.
Oh, these conditions. Gauge fixing conditions, you mean?
If it doesn't affect the physical reality.
It's kind of, you are trying to avoid double counting in a sense. In mathematics, it's called the equivalence classes. The gauge transformation just defines a family of equivalent functions which give the same electric and magnetic field. And the gauge fixing conditions just tell you which one to use as a representative of your equivalence class. Have you heard of quantum Hall effect?
Yeah. Or just
Some people are trying to understand some of the phenomena appearing in quantum Hall effect using this paraphase. This Aharonov-Bohm effect.
appearing. Appearing.
Appearing. So you see, because they already have the magnetic field in quantum Hall effect. So the Hall effect, the classical Hall effect is you just take a metal strip, put it in a magnetic field, a strong magnetic field, send a current through it. If you just consider an electron, the electron will be moving in the opposite direction. So the electron will feel a force due to the magnetic field, so the electron will be pushed upward. And so the upper edge will be negatively charged, the lower edge will be positively charged. So if you measure A and B, there will be a potential difference between A and B. Not along the current, perpendicular to the current. Well, if you have any resistor, there is a potential difference along the current. But this, in the presence of the magnetic field, you also get a potential difference perpendicular to the current. Well, this is the classical example. But now, with the current technologies, we can construct not necessarily such strips, but we create like many contacts, small contacts, connected to wires that can tunnel through various other wires. So on these lines are the conducting regions. And so here, this is not a conducting region. So the electrons will not be able to go through them. They can go up or down, and the conduction properties depends on the magnetic field because of this paraphase. Because when you cross this region, if there's a destructive interference on the other side, the electron just cannot go. If there's there's a destructive interference, the electrons cannot go. If there's a constructive interference, the electrons can pass through. And this is another kind of measurement of this paraphase. Well, of course, in this one, the magnetic field is everywhere, so you cannot really say that it is. I mean, the particles are far away from the magnetic field, but nevertheless, the basic idea is to say it's just this phase that the particles feel if they just go through different paths.
So by controlling the magnetic field, you can choose which way the electron.
Sure.
So it's basically a gate.
In a sense, I think so. I mean, I'm not an expert on quantum Hall effect, but that is what I understand from my friends working on that. We had a seminar on Wednesday on this one. We had a seminar on these things on Wednesday.
What is the parameter which, for very phase, we have a parameter which comes back to its initial state?
Sure. Well, in a sense, we have our Hamiltonian, which depends on certain parameters. Those parameters change as a function of time, but you just look at a region at the end of which your Hamiltonian is back to your initial Hamiltonian. In this one? In this one? Well, I don't know. I mean, you can just look at it in this form over here. So you see the phase difference. Where is the graph? Yep. The phase difference appearing over here is between the wave packet that moves in this direction and the one that moves below the ring. But you can also say it's the same phase difference as you would take a particle around this loop. So it's basically this geometry over here in that circle. So the particles can take various paths above or below. And this one also, the particles can go below, tunnel below, or above this region over here. And there's magnetic field in that region. And it is the flux in that region that controls whether there is a constructive or destructive interference on the other side. Okay, any questions? The wave function. Well, I mean, you can always have the statistical interpretation of the wave function. So you can say that there are many electrons in this system that whose wave functions are interfering on the other side. So the wave function of each electron is interfering on the other side, but you are basically seeing the electrons on the other side, not a single one or not. So I will stop here for today.
But it will be still true if there will be one electron.
Sure. But then you cannot see the pattern. You either see an electron or not. Well, you can send electrons one by one and you will still have the same pattern. I think that, and not in this setup, but that single electron interference is also done experimentally. I think it was Toshiba. I think it was the Toshiba who did the experiment. Industry company.
They don't pass the electron.
Hmm?
If the electrons cannot pass through this magnetic field and distract the interference, do they accumulate on one side or something?
It becomes an insulator.
This side.
So by changing the magnetic field strength, you control whether this is an insulator or a conductor. Or you can say that certain regions will become insulators, certain other regions become conductors.
What kind of transistor?
Well, I mean, these things work in a huge magnetic field under very cold temperatures.
Oh, really?
So the magnetic fields are several Teslas. The temperature is in the millikelvin temperature. So probably not a nearby technological application. Now this quantum Hall effect is interesting because if you measure the let's say the potential over the current is a kind of a resistance. So this is called the Hall resistance. And what I think they plot this, if you plot this Hall resistance as a function of magnetic field or some other parameter, you start to see plateaus. And those plateaus are very precisely, you can, I mean, I think the differences in those plateaus, I think it is h bar over E, or some constant like that. And they are fixed. So this is kind of the von Klitzing constant. He got the Nobel Prize for this. And basically this is another way of defining h bar, or E, if you like. So for example, for the speed, we already have a way of measuring. I mean, it's like the light. What is h bar? Well, this is, we can determine h bar, measure h bar. Or if you know h bar, you can determine E from this. In fact, I think the most precise measurement of E is from here. Anyway, this is kind of a subject which I'm not an expert on. I might be talking about something completely nonsense. Just check the relevant resources if you are interested.